Alright, we are finding the volume of solids with known cross-sections. Let's look at this example. Find the volume of a solid whose base is the region bounded by the lines blah and blah and blah, and whose cross-sections are perpendicular to the x-axis, are equilateral triangles. Step number 1. I'm going to draw the base. This is the top-down view of the solid shape. So I have my... Oh, didn't mean to do that. Here we go. That's fun. I didn't know I could do that. Okay, I have my x and y axis. I'm going to draw f of x. I've got an intersection of 1, and then my slope is going to go down 1 over 2. So there's f of x. And then g of x has a y-intercept of -1. It's going to go up 1 over 2. Can we just admire this for a second? I think that went pretty well. And x equals 0, which is the y-axis here. And so the region enclosed by those lines is this little triangle right here. So that's your first step. Draw your base. Step number 2 is draw a cross-section, or at least imagine it. You don't have to do this part, but it's helpful to kind of see what we're doing here. I know that the cross-sections perpendicular to the x-axis are equilateral triangles. So what I'm going to do is I'm going to take my xy axis here. I'm going to kind of tilt it sideways. So now this is sort of an aerial view where I had this enclosed region. It says the cross sections are equilateral triangles. So if I were to draw a cross section, base would be here, and then if you can imagine this in 3D, it comes up as an equilateral triangle. So there's a 3D shape here. This equilateral triangle. If I were to pick a cross section that was closer to here, it wouldn't be as big. So you can imagine if I filled this in entirely with all these equilateral triangles, I might end up with a shape that looked something like this. I might end up with this 3D shape here. And we want to find the volume of that 3D shape with these equilateral triangles inside it, right? So what I'm going to do is I'm going to go back to my picture of the base, and I'm going to draw just a representative cross-section. It would have a base, say, right here. There's my representative cross-section. And this has a length from here to here. We'll call that length L. Step number 4 is I'm going to draw a side view of my cross-section. So if I take that equilateral triangle and I draw it here, I want to label the sides of this cross-section in terms of L. What I drew on that graph was the base right here, and it had a length of L. And because this is an equilateral triangle, I know this side is L and this side is L. Now what I want to do is I want to find the area of my cross-section. The AP test expects you to know the area for an equilateral triangle. I confess I had to look it up, but it comes up over and over again. This is worth committing to memory. The area of an equilateral triangle is the square root of 3 over 4 times L squared. So I've written the area of my cross-section in terms of L, but now what I want to do is I need to plug in actual functions here for L. I'm going to go back to my figure here, and the question is, how can I write L in terms of my functions? And this is just like finding the area between two curves. I'm going to take the top function minus the bottom function and plug that in for L. And so here I see that the top function is f of x, the bottom function is g of x. And so get some space to work here. So L is going to be the top function minus the bottom function. And I can simplify this. Let me distribute that negative. That's a plus. And if I combine my like terms, I'll get 2 minus, that will become minus 2x over 2, or just x. That's a nice, convenient formula for L. Now what I want to do is I want to take this formula for L and plug it into my area formula. So my area is the square root of 3 over 4 times L squared. So this is the area of my cross-section in terms of my functions. To get the volume of the solid, what I want to do is I want to add up all of the cross-sections from x equals 0 to x equals 2. If I want to add up all the cross-sections, that means I want to integrate. So I'm going to take this function and integrate it from 0 to 2. Let's rewrite that and do it. So this is the integral from 0 to 2 of the square root of 3 over 4 times 2 minus x squared dx. First thing I'll do is pull my constants out front. And then looks like I will have to do u substitution. So I'll say u is 2 minus x, du is negative dx. And so when I rewrite that, I'm going to change my limits of integration. I want to change these. When I plug 0 in, I'm going to plug that in for x. When I plug 0 in for x, I will get 2. And when I plug 2 in, I will get 0. That'll make my life a little easier later on. So rewriting my integral, I have negative, because of that, I have negative square root of 3 over 4. Integral from 2 to 0, because I changed my limits, I don't have to go back to x now, of u squared du. You can go ahead and integrate. Carry my constant along, and that will be u cubed over 3, evaluated from 2 to 0. And so I have, if I plug in 0, I'll get 0 minus, now when I plug in 2, I still have my constant, times 2 cubed over 3. And then it's just a matter of simplifying, making it pretty. This negatives cancel out. We have square root of 3 over 4 times 8 over 3. That simplifies to 2 square root of 3 over 3. So to recap your steps here, step number 1 is draw your base. So graph your functions and draw your base. If you can imagine what the 3D shape looks like, it's not actually necessary to solving the problem, but it's nice to have a visual of what you're doing. The next step is to draw that cross-section, label its length L, and then to write L in terms of the function. Draw your cross-section, figure out the area of your cross-section in terms of L, and then plug in your function for L, and then integrate from the left to the right of whatever your base was.